Hello there, and welcome back to the Science Sleepy Minds. Picture this. You are floating, weightless, in a darkness so complete that the concept of direction has lost all meaning. There is no up, there is no down, there is only the hum of your own breathing and the faint, impossible cold of deep space pressing against your skin like a memory of winter. And then, slowly, something catches the edge of your vision, a shape, golden, hexagonal. 18 mirrors arranged like a honeycomb the size of a tennis court, each one polished to a smoothness measured in millionths of an inch. You're staring at the primary mirror of the James Webb Space Telescope, and it is staring back at you. Or rather, it is staring past you, deep into the oldest corners of the universe, where light has been travelling for so long that the stars that sent it may no longer exist. Tonight, we're going to talk about what that golden eye found out there. And fair warning, what it found is so strange, so fundamentally unsettling, that some of the smartest people on the planet are quietly losing sleep over it. You probably will not survive this one without drifting off yourself, which is sort of the point. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Also, drop a comment telling me where you are listening from and what time it is where you are. I always love reading those. Someone is always tuning in from a time zone I forget exists. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You need to understand something about the James Webb Space Telescope before we go any further. It is not just another telescope. Calling it that is like calling the ocean a puddle. Every generation or so, humanity builds an instrument so profoundly more capable than anything that came before it, that the very act of turning it on rewrites what we think we know. The optical telescope did it in the 1600s. Radio astronomy did it in the 1930s. The Hubble Space Telescope did it in 1990 when it launched aboard the Space Shuttle Discovery, and, after an embarrassing mirror fix, began sending back images that made grown astrophysicists weep openly at press conferences. But Hubble, for all its majesty, has limits. It sees primarily invisible and ultraviolet light. That means the oldest, most distant objects in the universe. The ones whose light has been stretched by the expansion of space itself into wavelengths our eyes cannot detect, remain hidden from Hubble's view. It is like trying to eavesdrop on a conversation happening 3 rooms away. You can hear murmuring, but you cannot make out the words. Webb was designed to hear the words. The telescope's primary instrument suite operates in the infrared. Infrared light is essentially heat radiation, the kind of light that objects emit when they are warm, the kind that gets stretched out of visible range when it travels across billions of light years of expanding space. By tuning its ears, so to speak, to this specific frequency, Webb can detect light that left its source over 13 billion years ago. It can see the faint, ruddy glow of the very first galaxies that ever formed. It can peer through curtains of cosmic dust that are completely opaque to Hubble. And it can analyze the atmospheres of planets orbiting distant stars, sniffing out molecules like water vapor and carbon dioxide with a sensitivity that borders on the absurd. One quirky detail that rarely makes it into the headlines is that Webb's sunshield, the 5-layered membrane that keeps the telescope cold enough to function, is roughly the size of a tennis court, yet each layer is thinner than a human hair. Engineers joked during development that it was essentially an extremely expensive kite. Scholars still debate whether the final design was the optimal configuration, or whether budget constraints forced compromises that future missions will need to correct. But here is the thing that keeps you up at night, or rather, the thing that would keep you up if you were not specifically trying to fall asleep. Within weeks of Webb becoming fully operational in the summer of 2022, the data started coming back. And it was wrong. Not wrong in the sense that the instruments were malfunctioning. The calibrations were perfect. The mirrors were aligned to within nanometers. The sun shield was holding temperature at a brisk minus 230 degrees Celsius. No, the data was wrong in the sense that the universe it was describing did not match the universe we thought we lived in. The images showed objects that were too big, too bright, too far away, too early. Galaxies that had no business existing in the time and place where Webb found them were sitting there, fat and smug and fully formed, like a toddler who somehow shows up to kindergarten with a doctoral degree and a mortgage. Astronomers ran the numbers again. They checked the calibrations again. They quietly asked colleagues at other institutions to double-check their work. The answer kept coming back the same. Something out there is breaking the rules, and the rules it is breaking are the ones we were most confident about. So you lie here in the dark and you let that thought settle over you like a blanket. The universe is not what we thought it was. The golden eye has seen something. And now, so will you. You might be wondering why anyone would spend 25 years and $10 billion building a single telescope. That is not a typo. 10 billion. With a B. The kind of number that makes budget committees physically uncomfortable and causes senators to develop sudden passions for fiscal responsibility. But to understand why Webb exists, you need to understand what came before it, and more importantly, what came before it could not do. Hubble launched in April of 1990 aboard the Space Shuttle Discovery. It was supposed to be humanity's greatest eye on the cosmos, and it was eventually. But first it had to survive one of the most humiliating engineering blunders in the history of space exploration. The primary mirror, the heart of the entire instrument, had been ground to the wrong shape, not by a lot. By about 2 microns, which is roughly 1/50th the width of a human hair. But in optics, 2 microns might as well be 2 miles. The first images Hubble sent back were blurry. Not poetically blurry, not artistically soft focus, just blurry. Like someone had smeared petroleum jelly on the lens of a $10 billion camera. Late-night comedians had a field day. Congress grumbled. NASA engineers quietly died inside. It took a servicing mission in 1993 to install corrective optics, essentially giving Hubble a pair of glasses, and after that the telescope began delivering the kind of images that change the way a species thinks about itself. Deep fields, pillars of creation, galaxies colliding in slow motion over hundreds of millions of years. Hubble showed us that the universe was not just vast but violently, absurdly, almost comically vast. But Hubble has a fundamental limitation. It sees mostly invisible and near ultraviolet light. That is fine for observing objects within a few billion light years, but the oldest light in the universe has been stretched by the expansion of space into infrared wavelength that Hubble simply cannot detect. Imagine trying to listen to a symphony, but your ears can only hear the high notes. You would get the violins and the flutes, but the cellos and the bass drums would be completely silent to you. That is Hubble's problem. The cellos of the cosmos, the deep, ancient infrared notes of the earliest galaxies, were invisible to it. Astronomers knew this. They had known it since the 1980s, and so, even before Hubble launched, people were already sketching plans for its successor, a telescope that could hear the bass. The project that would become the James Webb Space Telescope began its formal life in 1996, when a committee of astronomers recommended that NASA build a large infrared space telescope. The original name was the Next Generation Space Telescope, which sounds like a starship from a science fiction show, and was eventually changed to honour James Webb, the NASA administrator who oversaw the Apollo program during the 1960s. That naming choice, incidentally, became its own controversy decades later when researchers raised questions about Webb's role in government policies that discriminated against LGBTQ employees during the Lavender Scare era. Historians still argue whether Webb was an active participant in those policies or merely a bureaucratic bystander in a system that was rotten from the top down. NASA investigated, kept the name, and the debate continues in academic circles to this day. The engineering challenges were staggering. Because Webb needed to detect faint infrared light, it had to be kept extraordinarily cold. Any warmth from the telescope itself, from its electronics, from the sun, even from the Earth, would drown out the signals it was trying to capture. This is like trying to photograph a firefly while standing next to a bonfire. The solution was the sun shield, that tennis court-sized membrane we mentioned earlier, 5 layers of a material called Kapton, each coated with aluminum and treated silicon. Together, they would block the sun's heat so effectively that the difference in temperature between the sun-facing side and the instrument side would be roughly 300 degrees Celsius. The hot side would bake at about 85 degrees Celsius. The cold side would chill to minus 233. One fun detail that engineers love to share during development is that if you could somehow stand on the cold side of the sun shield, you could comfortably hold a snowball without it melting, assuming you could survive the vacuum and the radiation and the existential dread of being 1,000,000 miles from the nearest cup of coffee. Then there was the mirror. Hubble's mirror is 2.4 meters across. Webb's needed to be 6.5 meters to collect enough faint infrared light. But you cannot fit a 6.5 meter mirror inside any existing rocket fairing. So the engineers designed the mirror to fold. 18 hexagonal segments, each made of beryllium and coated with a microscopically thin layer of gold, would launch in a compact configuration and then unfurl in space like a mechanical flower. Every segment had to be aligned with every other segment to within 1/10,000th the width of a human hair. There were over 300 single points of failure in the deployment sequence. 300 moments where one stuck hinge, one jammed motor, one frayed cable could turn the most expensive scientific instrument ever built into the most expensive piece of space debris ever created. The launch happened on Christmas morning 2021. An Ariane 5 rocket lifted off from French Guiana carrying humanity's best hope for understanding the early universe. Mission control was tense in the specific way that only people who have spent 2 decades of their careers on a single project can be tense. The rocket performed flawlessly. The separation was clean. And then, over the following 2 weeks, Webb began to unfold. The sun shield deployed, the mirrors locked into place, the instruments cooled to operating temperature. Each step was confirmed with quiet applause and the kind of relieved sighs that sound almost like sobs. By late January, Webb was fully deployed at its destination, a gravitationally stable point called L2, roughly 1.5 million kilometers from Earth. Far enough that no servicing mission could ever reach it. Whatever they had built, whatever they had sent, that was it. There were no second chances. And now you lie here, breathing slowly, feeling the warmth of your blanket against the impossible cold of that distant instrument. It worked. All 300 opportunities for failure, and none of them happened. The golden eye opened, and what it saw would make the people who built it question everything. The first image arrived on July 11th, 2022, and it was released in an unusual way. The President of the United States stood at a podium in the White House and unveiled it during a live broadcast. This was not standard procedure for astronomical data. Normally, telescope images get published in journals, discussed at conferences, shared in press releases that most of the public never reads. But this image was different. NASA knew it was different, and they wanted the world to see it the way you see a sunrise, all at once, with no warning, just light flooding in. The image is called Webb's first deep field, and it shows a galaxy cluster called SMACS 0723 as it appeared roughly 4.6 billion years ago. The cluster itself is massive, a gravitational heavyweight bending space-time around it like a bowling ball sitting on a trampoline. But the cluster is not the star of the show. Behind it, distorted and magnified by the cluster's gravity, are thousands of galaxies. Thousands. And they're crammed into a patch of sky so small that if you held a grain of sand at arm's length, the grain would cover it. You could stand on a beach and pick up a single grain between your fingertips, hold it up against the night sky, and behind that tiny speck of silica, there would be entire civilizations, entire histories, entire cosmic dramas playing out across billions of years. That is the scale we are dealing with now. It is the kind of thought that makes your brain feel slightly carbonated. The reaction among astronomers was immediate and honestly, a little emotional. Many of them had spent their entire careers waiting for this telescope. Some had been graduate students when Webb was first proposed and were now senior professors with grey hair and tenure, and grandchildren who kept asking them to explain black holes at Thanksgiving dinner. Seeing the first image was not just a professional milestone. It was the fulfillment of a promise that science had made to itself a quarter-century earlier. One astronomer described the moment as similar to putting on glasses for the first time and realizing that trees have individual leaves. Hubble had shown them the forest. Webb was showing them the bark, the veins in the leaves, the insects crawling along the branches. But something was lurking in that image, something that did not fit. Among the thousands of background galaxies stretched and warped by gravitational lensing, several appeared far too bright and far too structured for their apparent distance. They were not faint smudges. They were not the vague blobs you would expect from a time when the universe was barely out of its infancy. They had defined shapes, spiral arms, central bulges, signs of organised structure that should have taken billions of years to develop. And yet the redshift data, which we'll get into more deeply very soon, placed these galaxies at a time when the universe was only a few 100 million years old. To put that in perspective, the universe is roughly 13.8 billion years old. A few 100 million years after the Big Bang is like the first 2 weeks of a human life. You're supposed to be a wrinkly, screaming, barely conscious little thing at that point. You're not supposed to show up with abs, a briefcase, and a fully diversified stock portfolio. The anomaly did not announce itself with trumpets. It crept in through the data like a cat slipping through a cracked door. Researchers at multiple institutions began independently noticing the same thing. The photometric data, which measures how much light an object emits at different wavelengths, was pointing to galaxy masses that were absurdly high for their cosmic epoch. We are talking about galaxies with tens of billions of solar masses existing at a time when the universe had barely had time to form its first stars. The initial reaction was caution. Photometric redshifts, which estimate distance based on colour rather than spectral lines, can be unreliable. Maybe the instruments were being fooled by dust. Maybe the calibration models needed tweaking. Maybe there was some exotic foreground contamination throwing off the numbers. Astronomers are trained skeptics. They do not panic at the first weird data point. They pour another coffee, check their math, and quietly hope that the weirdness will resolve itself into something boring and explainable. But Webb kept looking, and the weirdness kept piling up. Over the following weeks and months, as more data streamed back from L2, the catalogue of anomalous objects grew. It was not one galaxy. It was not a handful. It was dozens, then hundreds. Each one sitting at a redshift that placed it impossibly early in cosmic history. Each one displaying a mass and structural maturity that existing models said should be flatly impossible. One particularly strange object, which would later be catalogued under the decidedly unglamorous name CEERS-93316, appeared to have a redshift of approximately 16.7, which would place it a mere 230 million years after the Big Bang. At that distance and that time, the universe was still mostly hydrogen and helium gas, still cooling from the blinding heat of its birth. There should not have been anything there to see, let alone a fully formed galaxy cheerfully going about its business like nothing was wrong. Here is a quirky little detail that gives you a sense of how these discoveries ripple through the scientific community. When the first preprint papers describing these impossible galaxies hit the Archive, which is the online server where physicists share papers before peer review, the download numbers broke records. Papers about high redshift galaxies that would normally attract a few hundred readers were suddenly being downloaded thousands of times in a single day. Astrophysicists who had spent their careers studying relatively quiet corners of the field suddenly found their inboxes flooded with interview requests. One researcher reportedly joked that the only time her phone had rung this much was when her wedding invitations went out with the wrong date. Scholars still debate whether these early detections represent a genuine crisis for cosmology, or whether they are the expected growing pains of a new instrument pushing into uncharted observational territory. That debate, as you will see, is far from settled, but lying here in the dark you can feel the weight of what that first image contained. Not just beauty, not just wonder, a question. A crack in the foundation of everything we thought we understood. The galaxies should not have been there. That is the simplest way to say it, and it is also the most unsettling. You can dress it up in technical language, talk about stellar mass functions and halo assembly timescales and hierarchical structure formation. But at the bottom of all that jargon sits a very plain, very stubborn fact. The universe made something too big, too fast, and nobody can explain how. To understand why this matters, you need to picture how galaxies are supposed to form. The standard story goes something like this. After the Big Bang, the universe was a hot, dense, nearly uniform soup of particles and radiation. Nearly uniform, but not perfectly uniform. There were tiny fluctuations, microscopic ripples in the density of matter, and these ripples were the seeds of everything that would come later. Over hundreds of millions of years, gravity slowly pulled the slightly denser regions together. Gas collected into clumps. The clumps merged into larger clumps. Eventually, the densest pockets collapsed under their own weight and ignited as the first stars. These early stars were monsters, hundreds of times more massive than our Sun, burning through their fuel in just a few million years before exploding as supernovae and scattering heavier elements into the surrounding gas. Those heavier elements mixed into new clouds, which collapsed into new stars, which formed small proto-galaxies, which merged with other proto-galaxies over billions of years in a slow, grinding hierarchical process that eventually produced the grand spirals and ellipticals we see in the nearby universe. The key word in all of that is slowly. Galaxy formation is supposed to be a patient business. You start with dust, you build grains, you build pebbles, you build boulders. You do not wake up one Tuesday morning and find a mountain range where yesterday there was a parking lot. But that is essentially what Webb found. The galaxies sitting at redshifts between roughly 10 and 16 are not proto-galaxies. They are not the fragile, wispy, barely there structures that models predict for that era. They are mature. Some of them contain stellar populations that appear to be hundreds of millions of years old, which means the stars inside them must have formed even earlier, pushing their origins back to a time perilously close to the Big Bang itself. Some of them have estimated stellar masses of 10 billion solar masses or more. Our own Milky Way, which has had 13 billion years to accumulate its stars, has a stellar mass of roughly 40 to 60 billion solar masses. These infant galaxies had already built up a significant fraction of the Milky Way's mass in a tiny fraction of the time. It is as if you planted an acorn on Monday, and by Friday you had a 300-year-old oak tree with a tire swing and a family of squirrels who had been living there for generations. The first major paper to sound the alarm was led by a team using Webb's NIRCam instrument, the near-infrared camera, which is the telescope's primary imaging workhorse. They identified a population of galaxy candidates at redshifts above 10 that were far more numerous and far more luminous than any theoretical model had predicted. The paper was careful, hedging its language with phrases like "if confirmed" and "pending spectroscopic verification," because astronomers know that extraordinary claims require extraordinary evidence, and photometric estimates can sometimes be fooled. But even with the hedging, the implications were explosive. If even a fraction of these candidates turned out to be real, the standard model of galaxy formation would need serious revision. And then the spectroscopic confirmation started rolling in. Spectroscopy is the gold standard for measuring cosmic distances. Instead of estimating a galaxy's redshift from its colours, which is a bit like guessing someone's age from a blurry photograph, spectroscopy spreads the galaxy's light into a detailed spectrum and identifies specific emission or absorption lines from known elements. When you see the unmistakable fingerprint of hydrogen or oxygen shifted to a precise wavelength, you know exactly how far that light has been stretched, and therefore exactly how far away and how far back in time you're looking. One by one, candidates were confirmed, objects that the cautious community had hoped might turn out to be nearby interlopers, reddened by dust rather than distance, were verified as genuinely ancient, genuinely massive, and genuinely problematic. One particularly dramatic confirmation involved a galaxy called JADES-GS-Z13-0, which spectroscopy placed at a redshift of 13.2. That means the light Webb captured left that galaxy roughly 320 million years after the Big Bang. At that moment in cosmic history, the universe had completed barely 2% of its current age. And yet this galaxy was there, assembled, star-forming, structurally coherent. Historians of science have compared the reaction to the discovery of the cosmic microwave background in 1965, when Arno Penzias and Robert Wilson accidentally detected the afterglow of the Big Bang using a radio antenna in New Jersey, and initially thought the signal was caused by pigeon droppings on the equipment. That discovery confirmed the Big Bang theory. This one might end up challenging the framework that was built on top of it. There is a quirky footnote to the naming conventions here that gives you a window into how astronomers think. The acronym JADES stands for the JWST Advanced Deep Extragalactic Survey, which is about as dramatic as a tax form. Meanwhile, CEERS stands for the Cosmic Evolution Early Release Science Survey, which sounds slightly more exciting but still reads like something a committee designed by another committee would produce. Astronomers are brilliant at peering across the universe, but genuinely terrible at naming things. Scholars still argue whether the current naming system helps or hinders public engagement with these discoveries, a debate that is entirely academic and also entirely correct. You lie here and you let the strangeness of it wash over you. Galaxies that should not exist, stars that formed too early, a universe that apparently did not read its own instruction manual, and somewhere out at L2 the Golden Mirror keeps collecting photons, each one carrying a secret from the dawn of time, each one quietly insisting that the story we have been telling ourselves is missing a chapter. So what exactly is this instruction manual that the universe seems to have ignored? You hear the phrase, standard model of cosmology, tossed around in documentaries and podcast episodes and late-night Wikipedia spirals, but most people have only a vague sense of what it actually means. It sounds authoritative, It sounds settled. It sounds like the kind of thing that sits on a shelf in a leather-bound volume and does not appreciate being questioned. And for the better part of 2 decades, it earned that reputation. But now the leather is cracking and the pages are starting to come loose, and the universe, as it turns out, may have been writing in a different language all along. The official name is the Lambda CDM model, and it is the closest thing cosmology has to a grand unified theory of everything large. Lambda refers to the cosmological constant, which is the term physicists use for dark energy, that mysterious force that appears to be accelerating the expansion of the universe. CDM stands for cold dark matter, the invisible stuff that does not emit or absorb light, but whose gravitational influence shapes the large-scale structure of the cosmos. Together, Lambda and CDM describe a universe that is roughly 68% dark energy, 27% dark matter, and 5% ordinary matter. 5%. Everything you have ever seen, touched, tasted, loved, hated, stubbed your toe on, every star, every planet, every slice of pizza that has ever existed, all of it makes up about 5% of the total cosmic budget. The rest is darkness, and we're not even sure what kind of darkness it is. Lambda CDM has been extraordinarily successful. It predicted the patterns in the cosmic microwave background radiation, that faint afterglow of the Big Bang measured with exquisite precision by satellites like COBE, WMAP, and Planck. It predicted the distribution of galaxies across the sky, the way they cluster into filaments and walls and voids like soap bubbles in a cosmic bath. It predicted the relative abundances of hydrogen, helium, and lithium forged in the first few minutes after the Big Bang, a process called Big Bang nucleosynthesis that remains one of the most impressive quantitative successes in all of science. When a model gets that many things right, you tend to trust it. You build careers on it. You fund entire research programs around it. You print it on motivational posters and hang it in the hallways of physics departments, though admittedly that last one might just be Caltech. But Lambda CDM also makes very specific predictions about how structure forms in the universe. It says that the first objects to collapse under gravity were small, dark matter halos, clumps of invisible matter a few million times the mass of the Sun. These halos acted as gravitational scaffolding, attracting ordinary gas, which then cooled, condensed, and formed the first stars. Over time, small halos merged to form larger halos, small galaxies merged to form larger galaxies, and the cosmic web of structure grew in a bottom-up fashion, piece by piece, merger by merger, like a city expanding outward from a few original settlements. This is called hierarchical structure formation, and it is one of the pillars of the standard model. It is elegant, it is intuitive, it matches the behaviour of dark matter in computer simulations that have been running since the 1980s, and the galaxies that Webb found at redshifts above 10 are driving a truck through it. Here is the specific problem. In Lambda CDM, the amount of stellar mass that can assemble in a given volume of space by a given time is constrained by the amount of dark matter available and the efficiency with which gas can cool, collapse, and form stars. These constraints produce an upper limit on how massive a galaxy can be at any given epoch. At a redshift of 12, for example, the most massive galaxies the model allows should contain perhaps 100 million solar masses of stars, maybe 1 billion if you push the parameters to their extremes and squint generously at the error bars. But Webb is finding galaxies at that redshift with 10 billion solar masses. That is not a gentle disagreement. That is not a small tension that can be smoothed over with a tweak to the star formation efficiency parameter. That is an order of magnitude discrepancy, and in physics, an order of magnitude is the difference between a firecracker and a stick of dynamite. The analogy that keeps circulating among cosmologists is an architectural one. Imagine you have a well-tested theory of urban development that says it takes at least 50 years for a village to grow into a city. You have historical data from hundreds of cities around the world confirming this timeline. Then one day you fly over a piece of empty farmland that was photographed from the air just 2 years ago, and sitting there is a sprawling metropolis with skyscrapers, highways, a functioning subway system, and a Starbucks on every corner. You would not shrug and say, well, maybe they built quickly. You would question whether your theory of urban development was missing something fundamental. That is where cosmology finds itself right now. And here is a genuinely fringe tidbit that has been gaining traction in some theoretical circles. A small group of physicists has proposed that the answer might involve what they call stochastic star formation bursts, random episodes of insanely rapid star formation triggered by conditions in the early universe that do not occur today. In this picture, the first galaxies did not grow steadily. They exploded into existence in brief, violent flares of stellar production, assembling in a few tens of millions of years what normally takes billions. It is a speculative idea, and the community is divided on whether the physics actually supports it. Scholars still argue whether these burst models can be reconciled with the chemical enrichment patterns observed in ancient stellar populations, or whether they simply trade one mystery for another. You're sinking deeper into the pillow now, and the thought settles into you like sediment to a riverbed. The framework that explained nearly everything is struggling to explain this. The scaffolding that held the cosmos together in our equations is wobbling, and the telescope that was built to answer questions is, for the moment, doing something far more dangerous. It is asking new ones. You've been hearing the word redshift whispered through this story like a recurring motif in a piece of music, and now it is time to sit with it properly. Because redshift is not just a technical term that astronomers throw around to sound impressive at dinner parties, it is the key that unlocks everything Webb is doing. It is the reason the telescope can peer backward through time. And it is, when you think about it long enough in the dark with your eyes half closed, one of the most beautiful ideas in all of physics. Start with something familiar. You're standing on the side of a road, and an ambulance is approaching you with its siren wailing. As it gets closer, the sound waves compress, the pitch rises, and the siren sounds higher than it actually is. Then the ambulance passes you and drives away, and the sound waves stretch out behind it, the pitch drops, and the siren sounds lower. This is the Doppler effect, and you have experienced it 1,000 times without thinking about it. Christian Doppler first described it mathematically in 1842, working with sound waves and musicians in the Netherlands, which is a historical fact that feels almost too charming to be real. He literally used trumpeters on a moving train to test his theory. Scientists standing on the platform listened as the train approached and receded, confirming that the pitch shifted exactly as predicted. Scholars still argue whether Doppler fully understood the implications of his own discovery for light, or whether that conceptual leap had to wait for later physicists to complete. Now take that same principle and apply it to light instead of sound. Light, like sound, travels in waves, and those waves have a measurable wavelength. Short wavelengths look blue, long wavelengths look red. If a light source is moving toward you, the waves compress and the light shifts toward the blue end of the spectrum. If it is moving away from you, the waves stretch, and the light shifts toward the red end. This is redshift and blue shift, and they work exactly the same way as the ambulance siren, just with photons instead of pressure waves. But here is where the universe does something sneaky. The galaxies that Webb is observing are not really moving through space away from us, not in the conventional sense. They are sitting more or less still in their local patch of the cosmos, minding their own business. What is happening is that space itself is expanding, The fabric of the universe, the actual metric of distance between objects, is stretching like the surface of a balloon being inflated. And as space stretches, the light travelling through it stretches too. A photon that started its journey as ultraviolet light, short wavelength, high energy, blue, gets pulled and elongated by billions of years of cosmic expansion, until by the time it reaches Webb's detectors, it has become infrared light, long wavelength, low energy, red. The longer the light has been travelling, the more it has been stretched. The more it has been stretched, the higher the redshift, so when astronomers say a galaxy has a redshift of 13, they are saying that the light from that galaxy has been stretched by a factor of 14. It left as one kind of light and arrived as something completely different. It is like mailing a letter and having it arrive as a postcard. The message is the same, but the medium has been transformed by the journey. This is why Webb was built to see in infrared. The most ancient light in the universe, the light from the first stars and the first galaxies, was originally emitted in visible and ultraviolet wavelengths. But 13 billion years of expansion have stretched it into the infrared. Hubble, with its visible light eyes, could catch the tail end of this stretched light, the slightly reddened glow of galaxies out to about redshift 11 if it squinted hard enough. But beyond that, the light had been pushed entirely out of Hubble's range. Webb, with its gold-plated mirrors optimized for infrared, can see all the way out to redshifts of 20 or more, at least in theory. It is like upgrading from a radio that only picks up FM to one that also receives AM shortwave, and that one weird frequency, where you can hear air traffic control if the weather is right. One quirky detail about redshift that often gets overlooked is that it does not just tell you distance, it tells you time. Because light travels at a finite speed, looking at a galaxy at redshift 13 is the same as looking at a galaxy as it appeared 320 million years after the Big Bang. The light took 13.4 billion years to reach us. So Webb is not just a telescope, it is a time machine. Every photon it captures is a fossil, a preserved fragment of a moment that existed billions of years before Earth, before the Sun, before the Milky Way had finished assembling itself. You are not looking at the universe as it is. You're looking at the universe as it was, and the deeper you look, the further back you go. And this is precisely what makes the impossible galaxy so disturbing. When Webb reports a galaxy at redshift 16, it is not making a casual observation. It is saying that it found a fully formed, massive, star-filled structure at a time when the universe was barely 230 million years old. The models say this cannot happen. The physics of gas cooling and gravitational collapse and star formation do not work fast enough. It is as if someone handed you a photograph of your great-great-grandmother at age 2, and in the photograph she's wearing a graduation cap and holding a PhD thesis. The photograph is not fake. The camera is functioning perfectly, so either the photograph is lying, or your understanding of how people grow up is incomplete. There is a meditative quality to redshift that suits this hour of the night. The idea that light can be transformed by its journey, that the universe impresses its own history onto every photon that passes through it, that nothing arrives unchanged. You're lying here, and the light from your phone or your screen is reaching your eyes at its original wavelength, because the distance is trivially small. But somewhere out there, a photon that started as a burst of ultraviolet from the surface of one of the first stars ever born has been travelling for over 13 billion years, slowly reddening, slowly stretching, carrying its tiny message through the expanding dark. And tonight, or on some night very much like it, that photon landed on one of Webb's 18 golden mirrors and was measured, catalogued, and added to the growing pile of evidence that the universe is stranger than we dared to imagine. Your breathing slows, your eyelids feel heavy, and the light keeps travelling, and so does the trouble. Because the impossible galaxies are not the only crack in the cosmic windshield. There is another problem, one that predates Webb by nearly a decade, and Webb has just made it worse. Much worse. It is called the Hubble Tension, and despite the name, it has nothing to do with the Hubble Space Telescope having a bad day. It has to do with the rate at which the universe is flying apart and the deeply uncomfortable fact that two perfectly valid methods of measuring that rate give two different answers. Let us back up for a moment and talk about the expansion of the universe itself. In 1929, Edwin Hubble, the astronomer not the telescope, published observations showing that distant galaxies are moving away from us, and that the farther away a galaxy is, the faster it is receding. This was the first direct evidence that the universe is expanding, a discovery so profound that it reshaped the entire trajectory of 20th century physics. Before Hubble's observation, most scientists, including Einstein himself, assumed the universe was static, eternal, and unchanging. Einstein had even added a fudge factor to his equations of general relativity, the famous cosmological constant, specifically to prevent his math from predicting an expanding universe. When Hubble proved that the universe was in fact expanding, Einstein reportedly called the cosmological constant his greatest blunder, which is ironic because decades later that same constant would come back in a very different form as the mathematical description of dark energy, but that is a thread we will tug on shortly. The rate of expansion is described by a number called the Hubble constant, denoted h0. It tells you how fast a galaxy at a given distance is receding from you. A higher h0 means the universe is expanding faster, a lower one means it is expanding slower. Measuring this number accurately has been one of the great obsessions of observational cosmology for nearly a century. And for most of that century, the measurements were rough enough that disagreements between different methods could be blamed on experimental uncertainty. The error bars were big and friendly and covered a comfortable range. Everyone could agree to disagree and go home happy. But then the measurements got better, significantly better, and the agreement fell apart. One method of measuring the Hubble constant works from the bottom up. You observe objects in the nearby universe whose intrinsic brightness you think you know, objects called standard candles. The most famous standard candles are Type 1a supernovae, which are thermonuclear explosions of white dwarf stars that all reach approximately the same peak luminosity. By comparing how bright a Type 1a supernova appears to be with how bright you know it actually is, you can calculate how far away it is. Do this for enough supernovae at enough distances, and you can build a distance ladder that stretches from the nearest stars all the way out to galaxies billions of light years away. From that ladder, you can measure the expansion rate directly. This is the approach championed by a team led by Nobel laureate Adam Rees, and their most recent measurements place h0 at roughly 73 km per second per megaparsec. The other method works from the top down. You start with the cosmic microwave background, that ancient afterglow of the Big Bang that pervades the entire sky. The patterns in the CMB are exquisitely sensitive to the conditions of the early universe, including the expansion rate. By feeding those patterns into the Lambda CDM model and running the equations forward to the present day, you can predict what the Hubble constant should be now. This is the approach used by the Planck satellite team, and their answer is roughly 67.4 kilometers per second per megaparsec. 73 versus 67.4. That might not sound like a big deal. It is about an 8% difference, but in precision cosmology, 8% is enormous. Both measurements have error bars that are now small enough that the ranges do not overlap. They are not within spitting distance of each other. They are genuinely, statistically, stubbornly incompatible. It is like two people measuring the height of the same building, one from the inside using a tape measure, and one from the outside using surveying equipment, and getting answers that differ by an entire floor. One of them has to be wrong. Or, and this is the option that keeps theorists up at night, maybe neither of them is wrong, and the building is just stranger than anyone realized. For years, the cosmology community hoped the tension was a systematic error. Maybe the supernova teams were slightly miscalibrating their distance ladders. Maybe the Planck team's model assumptions were slightly off. Maybe there was some subtle bias in the Cepheid variable star measurements used to anchor the bottom rung of the distance ladder. Cepheids, incidentally, are pulsating stars whose brightness varies in a regular cycle, and that cycle is directly related to their intrinsic luminosity. Henrietta Swan Leavitt discovered this relationship in 1912 while studying photographic plates at the Harvard College Observatory, working as one of the so-called human computers who were paid significantly less than their male colleagues and were not permitted to operate the telescopes themselves. That quirky historical detail carries a bitter edge, but Leavitt's discovery remains one of the foundational tools of modern distance measurement. Enter Webb. One of the telescope's early calibration projects was to observe Cepheid variables in nearby galaxies with unprecedented infrared precision. The hope for some was that Webb would reveal a systematic error in the Hubble Space Telescope's Cepheid measurements, perhaps caused by crowding effects where nearby stars blended together in Hubble's lower resolution images and skewed the brightness estimates. If that were the case, the tension might dissolve. The local measurement of H0 would shift downward, closer to the Planck value, and everyone could breathe again. It did not happen. Webb's Cepheid observations confirmed the Hubble Space Telescope's measurements almost exactly. The crowding was not the problem. The distance ladder was solid. The local value of H0 remained stubbornly around 73. Scholars still argue whether the remaining discrepancy points to new physics beyond Lambda CDM or whether some yet unidentified systematic error is hiding in one of the measurement chains. But with Webb's confirmation, the list of plausible systematic errors is getting very short, and the possibility that the universe itself is trying to tell us something new is getting very hard to ignore. You feel the weight of two incompatible numbers pressing gently on your chest. 73, 67. The universe expanding at two different speeds depending on how you look at it. And somewhere in the gap between those numbers, something fundamental might be waiting to be discovered. The gap between those two numbers is not just an accounting error, it might be a doorway. And what could be standing on the other side of that doorway is an idea so radical that even the physicists proposing it tend to do so with a slight wince, as if they are apologizing in advance for the mess they are about to make. The idea is this: dark energy, the force that is pushing the universe apart, might not be constant. It might be changing. And if it is changing, then nearly everything we think we know about the fate of the cosmos needs to be rewritten from scratch. Let us sit with dark energy for a moment, because it deserves more than a passing mention. It is, after all, 68% of the universe. More than 2/3 of everything that exists is this stuff, and we have almost no idea what it actually is. The story of its discovery begins in 1998, when two independent teams of astronomers were using Type 1a supernovae to measure the expansion history of the universe. They expected to find that the expansion was slowing down over time, which would make sense because gravity should be pulling everything back together, like a ball thrown into the air gradually losing speed. Instead, they found the opposite. The expansion was accelerating. The ball was not slowing down. It was speeding up. Something was pushing the universe apart with increasing force, and nobody had any idea what it was. The discovery earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011, which is the scientific equivalent of being handed a trophy for proving that reality is more confusing than anyone thought. The simplest explanation for dark energy is Einstein's cosmological constant, that old fudge factor he introduced and then regretted. In its modern incarnation, the cosmological constant represents a fixed energy density inherent to space itself. Every cubic meter of empty space contains a small but non-zero amount of energy, and as the universe expands and creates more space, there is more total energy pushing things apart. The beauty of this explanation is its simplicity. The cosmological constant is constant. It does not change over time. It does not vary from place to place. It just sits there, quietly and relentlessly inflating the universe like someone left the air pump running in a bouncy castle. Lambda CDM is built on this assumption. The lambda in the name is literally the cosmological constant. But there has always been a nagging problem with this picture. When physicists try to calculate what the cosmological constant should be based on quantum field theory, the theory that describes the behaviour of particles and fields at the smallest scales, they get an answer that is off by a factor of roughly 10 to the power of 120. That is not a typo. The theoretical prediction is a 1 followed by 120 zeros times larger than the observed value. This is often called the worst prediction in the history of physics, and it is genuinely difficult to overstate how embarrassing it is. Imagine predicting that your morning coffee would cost about $1 trillion dollars, and then discovering it actually cost $250. Something is clearly very wrong with either the prediction or the framework producing it, and nobody has been able to figure out what. This is where the new Webb data enters the conversation, arm in arm with results from other major surveys. In 2024, a collaboration called DESEI, the Dark Energy Spectroscopic Instrument, released preliminary results from its massive survey of galaxy redshifts. DESI is a ground-based instrument mounted on a telescope in Arizona that can measure the spectra of 5,000 galaxies simultaneously, mapping the three-dimensional distribution of matter across huge volumes of space. By studying how that distribution changes at different cosmic epochs, DESI can trace the expansion history of the universe with extraordinary precision, and what the early DESI results suggested tentatively but intriguingly is that dark energy might not be constant after all. The data hinted that the equation of state of dark energy, a parameter called W that describes the relationship between its pressure and its density, might be evolving over time. If W equals -1, dark energy behaves exactly like a cosmological constant. If W is something else, or if it changes, then dark energy is something more exotic, something dynamic, something with its own internal physics that we have not yet understood. Webb contributes to this picture by providing independent constraints on the expansion history through its observations of distant supernova and high redshift galaxies. When you combine Webb's data with DESI's data, and with the CMB measurements from Planck, the combined dataset starts to favour models in which dark energy varies, not overwhelmingly, not with the kind of statistical significance that makes physicists pop champagne, but enough to make them lean forward in their chairs and start writing grant proposals with slightly more urgency than usual. One historical parallel worth mentioning is the discovery of the cosmic microwave background itself. In 1964, Penzias and Wilson, the pigeon-troubled radio astronomers we mentioned earlier, did not set out to find the afterglow of the Big Bang. They were trying to calibrate a radio antenna for satellite communications and kept picking up a persistent hum that they could not eliminate. They cleaned the antenna, they removed the pigeons, they checked every connection and every cable. The hum remained. It was coming from everywhere in the sky, uniform and featureless. It took a conversation with theorists at Princeton for Penzias and Wilson to realise that they had accidentally discovered the most important signal in cosmology. Sometimes the universe tells you something by refusing to shut up. Scholars still argue whether the current hints of evolving dark energy will survive further scrutiny, or whether they are statistical fluctuations that will wash out as more data accumulates. The history of cosmology is littered with tantalizing hints that turned out to be noise, but it's also marked by a few pivotal moments where a small anomaly turned out to be the first thread of an entirely new understanding. And you are lying here in one of those moments, in the space between signal and noise, between discovery and disappointment, letting the uncertainty itself become a kind of lullaby. The universe might be changing its own rules as it goes, and that is either terrifying or beautiful, depending on how much sleep you have had. And while the cosmic expansion rate wobbles and dark energy flickers between constant and variable, there is another mystery brewing in the earliest epochs of the universe that Webb has dragged into the spotlight. The first stars, the ones that lit up the cosmos after the long darkness that followed the Big Bang. They were supposed to ignite slowly, reluctantly, like a damp campfire that takes forever to catch. Instead, Webb is finding evidence that they blazed into existence with a ferocity and a speed that nobody predicted. To understand why this matters, you need to know about the cosmic dark ages. This is not a metaphor. It is an actual period in the history of the universe, lasting roughly from about 380,000 years after the Big Bang to somewhere around 1 or 200 million years later. During this interval, the universe had cooled enough for the first atoms to form, hydrogen and helium nuclei capturing electrons and becoming neutral gas for the first time. But there were no stars yet, no galaxies, no sources of light at all. The cosmic microwave background had been released, its photons streaming freely through space, and after that initial flash the universe went dark. Completely dark. If you could somehow transport yourself to this era, you would float in a warm, expanding fog of hydrogen gas and see absolutely nothing. It would be like being inside a cloud, except the cloud is the entire universe, and there is no ground beneath you and no sky above you, and the nearest anything is millions of years away from happening. It is, in a way, the most peaceful moment in cosmic history, and also the most boring. Then the first stars formed, and everything changed. These primordial stars are called population 3 stars, which is a confusingly backwards naming convention that exists because astronomers classified the stars they could see first and worked backward. Population 1 stars are young, metal-rich stars like our Sun. Population 2 stars are older, metal-poor stars found in globular clusters and the halos of galaxies. Population 3 stars are the hypothetical first generation, formed from pure hydrogen and helium with essentially zero heavier elements, because no heavier elements had been created yet. Without heavier elements to help gas clouds cool efficiently, the physics of collapse is different. The clouds have to rely on molecular hydrogen as their primary coolant, which is far less efficient than the carbon and oxygen that later generations of stars use. This means the gas has to reach much higher temperatures and much higher masses before it can fragment and collapse. The result, according to standard models, is that population 3 stars should have been enormous, hundreds of times the mass of our Sun, possibly even 1,000 solar masses in extreme cases. They would have burned incredibly hot, incredibly bright and incredibly fast, living only a few million years before exploding as supernovae and seeding the surrounding gas with the first heavy elements. The universe's first act of creation was also its most violent. But here is where Webb complicates the narrative. The telescope's infrared sensitivity allows it to probe the chemical signatures of extremely distant galaxies, and some of those signatures are strange. Several high redshift galaxies show evidence of stellar populations that contain more heavy elements than they should at that point in cosmic history. If the first stars formed slowly and sparsely as models predict, There should not have been enough supernovae by that epoch to enrich the surrounding gas to the levels Webb is detecting. It is as if someone salted the soup before any salt had been mined. The chemical enrichment is too advanced for the timeline. One proposed explanation is that star formation in the early universe was far more efficient than models assume. Perhaps the gas fragmented into stars more readily. Perhaps the initial mass function, which describes the distribution of stellar masses at birth, was skewed even more heavily toward massive stars than we thought. More massive stars live shorter lives, explode sooner, and spread their heavy elements faster. If the first generation of stars was overwhelmingly dominated by monsters, the early chemical enrichment makes more sense. But this creates its own problems, because it means more energy was being pumped into the surrounding gas at earlier times, which would have ionized the neutral hydrogen and ended the cosmic dark ages sooner than the standard timeline suggests. There is a quirky and somewhat romantic detail about how astronomers search for population 3 stars. Because no population 3 star has ever been directly observed, not by Hubble, not by Webb, not by any instrument. Their existence is inferred entirely from theory and from the chemical fingerprints they left behind. Some researchers have spent their entire careers looking for a single unambiguous detection. It is a bit like being a cryptozoologist who studies footprints and broken branches but has never actually seen the creature. One team at the University of Tokyo has been running simulations for over a decade trying to predict exactly what spectral signature a population 3 star would produce if Webb happened to catch one in the act of dying. The signature involves an unusual ratio of helium emission lines and a near-total absence of metal absorption features. So far, no confirmed detection. But several candidates are being studied with the intensity of detectives examining a crime scene. Scholars still argue whether the early chemical enrichment Webb is detecting requires a fundamentally new model of first star formation, or whether adjustments to existing models can accommodate the data. The debate is lively, sometimes heated, and conducted primarily in the language of spectral energy distributions and nucleosynthetic yields, which sounds dry on paper, but represents one of the most consequential questions in astrophysics. How did the universe wake up from its dark ages? How did it go from silence to symphony? And why does it seem like the music started playing before the orchestra had finished tuning? You breathe in, you breathe out. Somewhere impossibly far away and impossibly long ago, the first star is igniting, and it is burning faster and brighter than anyone expected, throwing its light into a universe that has been waiting in the dark for millions of years. You know the feeling. Some mornings the alarm goes off and the darkness feels like it will last forever. And then, suddenly, light. The first stars were not the only things that appeared too quickly. There is something else lurking in Webb's data that is, if anything, even harder to explain. Black holes. Not the modest stellar mass black holes that form when a large star collapses at the end of its life. The kind that weigh perhaps 10 or 20 times the mass of the Sun and sit quietly in the galactic suburbs like retired wrestlers. No, Webb is finding supermassive black holes, the kind that weigh millions or billions of times the mass of the Sun, the kind that sit at the centres of galaxies and power quasars so luminous they outshine everything around them by a factor of 1,000. And it is finding them at redshift so high, at times so early, that the universe simply did not have enough time to grow them through any process we currently understand. The standard picture of black hole growth goes something like this. A massive star, maybe 50 or 100 times the mass of the Sun, exhausts its nuclear fuel and collapses. The core implodes past the point of no return and becomes a stellar mass black hole, perhaps 10 to 30 solar masses. This baby black hole then grows by accreting matter from its surroundings, pulling in gas and dust and occasionally swallowing smaller stars that wander too close. As the black hole feeds, the infalling material forms a superheated disk that radiates enormous amounts of energy. This is the accretion disk, and it is one of the most energetic environments in the universe, reaching temperatures of millions of degrees and glowing across the electromagnetic spectrum from radio waves to X-rays. The black hole grows as it eats, gradually building up mass over hundreds of millions or billions of years. But there is a speed limit. It is called the Eddington limit, named after the British astrophysicist Arthur Eddington, who in the early 20th century figured out that there is a maximum rate at which a black hole can accrete matter. Beyond that rate, the radiation pressure from the superheated accretion disk becomes so intense that it actually pushes the infalling gas away, shutting off the food supply. It is like trying to drink from a fire hose. Past a certain flow rate, the water pushes you backward instead of going into your mouth. The Eddington limit means that a black hole starting at, say, 100 solar masses can only grow so fast. Even if it feeds continuously at the maximum possible rate, never taking a break, never losing its appetite, it takes roughly 700 to 800 million years to reach 1 billion solar masses. That is a long time. But it is a specific, calculable time, and it sets a firm boundary on how massive a black hole can be at any given epoch. Now, here is the problem. Webb, along with complementary observations from ground-based telescopes and the Chandra X-ray Observatory, has identified supermassive black holes with masses exceeding 1 billion solar masses at redshifts above 10. That places them within the first 500 million years after the Big Bang. If you do the math, and many people have done the math with increasing desperation, there is simply not enough time for a stellar mass seed black hole to grow to 1 billion solar masses by that epoch, even at the maximum Eddington rate, even with continuous accretion, even with the most generous assumptions about seed mass and duty cycle. The numbers do not add up. You cannot get there from here. It is like discovering a fully grown sequoia tree in a forest that was planted last spring. The tree is real. The forest is real. The timeline is impossible. One of the most striking individual cases is a quasar identified in Webb data, at a redshift of approximately 10.6. This object is powered by a black hole estimated at several hundred million solar masses, possibly approaching 1 billion, existing at a time when the universe was barely 450 million years old. The light from this quasar has been travelling for over 13 billion years to reach Webb's detectors, and the black hole powering it is sitting there, fully assembled, cheerfully devouring its surroundings, utterly indifferent to the theoretical constraints that say it should not exist yet. The historical parallel here is worth noting. When the first quasars were discovered in the early 1960s by astronomer Martin Schmidt, they were so luminous and so distant that many scientists initially refused to believe the distance measurements were correct. The idea that an object could outshine an entire galaxy from a region smaller than the solar system seemed absurd. Schmidt himself later recounted that the moment he realized the redshift of quasar 3C273 corresponded to a recession velocity of nearly 16% the speed of light, he sat at his desk in stunned silence for several minutes. The discovery of quasars eventually led to the understanding that supermassive black holes exist and that they are common at the centers of galaxies. Now, 60 years later, Webb is pulling the same trick again, finding objects that challenge the imagination and force theorists back to the drawing board. And there is a quirky observational detail that makes these early black holes even more puzzling. Some of them appear to be overmassive relative to their host galaxies. In the nearby universe, there is a well-established relationship between the mass of a galaxy's central black hole and the mass of the galaxy's stellar bulge. The black hole typically contains about 0.1% of the bulge mass. This relationship is tight enough that it suggests a deep physical connection between how galaxies grow and how their central black holes grow, a kind of coevolution where each one regulates the other. But several of Webb's high redshift black holes seem to violate this ratio. Their masses are too high compared to the stellar mass of their host galaxies. The black holes appear to have outpaced their galaxies, arriving at maturity before their hosts had finished forming. Scholars still argue whether this means the coevolution relationship breaks down at high redshift, or whether the stellar mass estimates for the host galaxies are being underestimated due to dust obscuration or other systematic effects. The debate is vigorous and ongoing, and it touches on fundamental questions about the relationship between the brightest objects in the universe and the dark behemoths hiding at their cores. You're drifting now, and the image of a black hole assembling itself in the infant universe settles into your thoughts like a stone sinking through warm water. No childhood, no adolescence, just sudden, inexplicable maturity. The universe making monsters in the dark, and Webb catching them in the act. So how do you build a monster without giving it time to grow? That is the question that has launched 1,000 theoretical papers and at least as many heated arguments at conference coffee breaks. If the standard pathway of stellar collapse followed by gradual accretion cannot produce billion solar mass black holes in the first few 100 million years, then something else must be going on. And the proposals that theorists have put forward range from the elegantly plausible to the gloriously exotic, each one carrying its own set of predictions, its own set of problems, and its own flavour of beautiful strangeness. The most conservative proposal is called super-Eddington accretion. The idea here is that maybe the Eddington limit is not as firm as we think. Remember, the limit describes the point where radiation pressure from the accretion disk pushes in falling gas away, capping the feeding rate. But the derivation of the Eddington limit assumes spherical symmetry, meaning that the gas is falling in uniformly from all directions, and the radiation is pushing outward uniformly in all directions. Real accretion is not spherical, it is messy. Gas can funnel in through dense streams and filaments, while radiation escapes through thinner channels, perpendicular to the disk. If the geometry is right, the effective accretion rate can exceed the classical Eddington limit by factors of several, maybe even 10 or more. This would shorten the growth timescale significantly. A black hole that can eat 10 times faster reaches 1 billion solar masses in a fraction of the time. The physics is plausible, and some simulations support it. But even super-Eddington accretion has its limits. You can push the feeding rate up, but you cannot push it up indefinitely. The radiation still carries energy, the gas still heats up. At some point the system self-regulates regardless of geometry. And for the most extreme cases Webb has uncovered, even generous super-Eddington models struggle to close the gap. The second proposal is heavier seeds. Instead of starting with a stellar mass black hole of 10 or 30 solar masses, what if the initial seed was already much more massive? This is where the concept of direct collapse black holes enters the picture. In certain rare conditions in the early universe, it might have been possible for a massive cloud of primordial gas to collapse directly into a black hole without ever forming a star first. The key requirement is that the gas cloud must be prevented from fragmenting into smaller clumps, which is what normally happens when gas cools and condenses. If the cloud can be kept warm enough, typically by bathing it in a strong ultraviolet radiation field from nearby star-forming regions, it suppresses the molecular hydrogen cooling that would otherwise cause fragmentation. The entire cloud, perhaps 100,000 solar masses or more, collapses monolithically into a single enormous black hole. No stellar intermediary, no supernova. Just gas becoming gravity becoming darkness in one smooth, terrifying gulp. Direct collapse black holes are theoretically elegant and deeply appealing because they solve the timing problem in a single stroke. A seed of 100,000 solar masses needs far less time to reach 1 billion solar masses than a seed of 30. The arithmetic works. But the conditions required for direct collapse are extremely specific. You need a pristine gas cloud with no metals, because metals enhance cooling and promote fragmentation. You need a strong Lyman-Werner radiation background, which is ultraviolet light in a specific wavelength range that dissociates molecular hydrogen. And you need the cloud to be massive enough and dense enough to collapse before anything else disrupts it. The probability of all these conditions aligning in the same place at the same time is low. How low is a matter of active research and active argument. Some simulations suggest direct collapse events were common enough to explain the observed population of early supermassive black holes. Others suggest they were vanishingly rare, perhaps occurring only a handful of times in the entire observable universe. Then there are the more exotic ideas. One of the most intriguing involves dark matter itself. In the standard Lambda CDM framework, dark matter is cold, meaning the particles move slowly relative to the speed of light and interact with ordinary matter only through gravity. But some alternative models propose that dark matter particles can occasionally annihilate when they encounter each other, releasing energy. In the dense cores of early dark matter halos, where the concentration of particles is highest, this annihilation energy could heat the surrounding gas and prevent it from forming stars. Instead, the gas accumulates in the center of the halo, growing more and more massive until eventually it collapses into a black hole far more massive than any stellar remnant. These are sometimes called dark matter-powered black holes, or dark stars, which is a term that sounds like a prog rock album from 1973 and is in fact almost as speculative. The idea has its supporters, but it relies on specific assumptions about dark matter particle physics that remain unverified. One quirky historical footnote is that the concept of a black hole itself was considered fringe science for most of the 20th century. Einstein's field equations predicted their existence as early as 1915, when Carl Schwarzschild found the first exact solution describing the space-time geometry around a point mass. But Einstein himself never fully accepted that such objects could exist in nature. He thought they were mathematical curiosities, artifacts of the equations rather than features of reality. It took decades of theoretical work and observational evidence, culminating in the detection of Cygnus Azek-1 in the 1970s and the direct imaging of a black hole shadow by the Event Horizon Telescope in 2019, for the scientific community to fully embrace black holes as real, physical objects. Scholars still argue about the precise moment when the consensus shifted from skepticism to acceptance, but the irony is unmistakable. The objects that Einstein's own theory predicted, and that he refused to believe in, are now among the most studied and most enigmatic entities in the cosmos. And Webb is now finding them in places and at times where even the believers did not expect them. Each new detection tightens the constraints on theoretical models. Each new billion solar mass black hole at redshift 11 or 12 narrows the range of possible explanations. Somewhere in the space between super Eddington accretion and direct collapse and dark matter annihilation lies the truth, and Webb is slowly, patiently, photon by photon closing in on it. You settle deeper into the dark, you think about seeds, about things that grow, about how sometimes the most important question is not what something became, but how it began. The monsters at the centres of galaxies were once seeds, and the seeds, it turns out, might have been monstrous from the very start. The monsters can wait. Let us go somewhere gentler for a while. Because Webb is not only staring into the abyss of the ancient universe, hunting for impossible galaxies and inexplicable black holes, it is also doing something quieter, something more intimate, something that touches the question humans have been whispering into campfires and telescopes and each other's ears for as long as we have existed. Are we alone? And to pursue that question, Webb has turned its golden gaze toward the atmospheres of planets orbiting other stars. Exoplanet science is relatively young. The first confirmed detection of a planet orbiting a Sun-like star happened in 1995, when Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, a bloated gas giant orbiting absurdly close to its parent star. The discovery earned them a share of the Nobel Prize in Physics in 2019 and launched an entirely new field of astronomy. Before 1995, the existence of planets around other stars was widely assumed but unproven. After 1995, the floodgates opened. The Kepler Space Telescope, launched in 2009, spent years staring at a single patch of sky, monitoring the brightness of over 150,000 stars, watching for the tiny, periodic dips that occur when a planet passes in front of its star and blocks a fraction of its light. By the time Kepler's mission ended, it had discovered over 2,700 confirmed exoplanets and suggested that planets are not rare at all. They're everywhere. Statistically, every star in the Milky Way has at least one planet. There are more planets in our galaxy than there are stars. The universe is not a desert, it is a garden. But finding planets is only the first step. Knowing they exist tells you very little about what they are like. Are they rocky or gaseous, hot or cold, dry or wet? Do they have atmospheres? And if so, what are those atmospheres made of? These are the questions that matter if you care about habitability, and they are questions that Kepler, for all its brilliance, was not designed to answer. Kepler could tell you that a planet was there. It could tell you how big it was and how long its year lasted, but it could not sniff the air. Webb can sniff the air. The technique is called transmission spectroscopy, and it is one of the most elegant observational methods in modern astronomy. When a planet passes in front of its star, most of the starlight is blocked by the planet's solid body. But a tiny fraction of the starlight passes through the planet's atmosphere on its way to your telescope. As it does, certain wavelengths are absorbed by molecules in the atmosphere. Water vapor absorbs at certain infrared wavelengths, carbon dioxide absorbs at others, methane absorbs at still others. By comparing the star's spectrum when the planet is in front of it with the spectrum when it is not, you can identify which molecules are present in the planet's atmosphere. You're essentially reading the chemical recipe of an alien sky from dozens of light years away. It is like standing outside a restaurant, never going in, and deducing the entire menu by smelling the air coming through the ventilation system. Webb performed one of its first transmission spectroscopy observations on a planet called WASP-39b, a hot gas giant roughly the mass of Saturn, orbiting a star about 700 light-years away. The results were published in late 2022 and were, scientifically speaking, spectacular. Webb detected water vapor, carbon dioxide, sodium, potassium, and most notably sulfur dioxide in the planet's atmosphere. The sulfur dioxide detection was particularly significant because it is produced by photochemistry, chemical reactions driven by starlight interacting with the atmosphere. This was the first time photochemistry had been detected in an exoplanet atmosphere, and it demonstrated that Webb could not only identify what molecules were present, but also infer the chemical processes creating them. One slightly amusing detail is that sulfur dioxide is the same compound responsible for the smell of struck matches and volcanic fumaroles. So WASP-39b, in addition to being a scorching, uninhabitable gas giant with no solid surface, probably smells terrible. But the real excitement is not about hot Jupiters. The real excitement is about smaller, rockier worlds, planets closer to Earth's size, orbiting in the habitable zones of their stars, where liquid water could theoretically exist on the surface. Webb has begun observing several of these targets, and one result in particular sent a jolt through the exoplanet community. In 2023, Webb observed K218b, a planet roughly 8.5 times the mass of Earth orbiting in the habitable zone of a cool red dwarf star about 120 light-year away. The data revealed the presence of methane, carbon dioxide, and tentative hints of dimethyl sulfide in the planet's atmosphere. That last molecule is the one that raised eyebrows, because on Earth, dimethyl sulfide is produced almost exclusively by living organisms, primarily marine phytoplankton. It is, in the language of astrobiology, a potential biosignature. Now, before you sit up in bed and start composing a message to everyone you know, there are enormous caveats. The dimethyl sulfide detection was tentative, sitting at the edge of statistical significance. Follow-up observations are needed to confirm it. And even if it is real, there may be abiotic processes, non-biological chemistry, that could produce dimethyl sulfide under the right conditions on a planet very different from Earth. Scholars still argue whether dimethyl sulfide should be classified as a strong biosignature or a weak one, and the debate hinges on atmospheric modelling assumptions that are themselves uncertain. The planet is also likely not a rocky world with oceans. It is probably a Hessian world, a theoretical class of planet with a thick hydrogen atmosphere overlying a global water ocean, which is an environment with no analogue in our solar system and whose chemistry is poorly understood. But still, a molecule associated with life, detected in the atmosphere of a planet in the habitable zone, over 100 light-years away. Even as a tentative result, it represents something extraordinary. It is not proof of life. It is not even strong evidence of life. But it is the kind of clue that makes you hold your breath, the kind that makes the silence of the universe feel a little less empty and a little more expectant. You lie here and you think about phytoplankton. Tiny microscopic creatures drifting in Earth's oceans, exhaling a molecule that floats up through the atmosphere, and billions of years from now, might be the fingerprint by which some distant telescope recognizes that this world was alive. And then you think about K218b, 120 light-years away, and whatever might be drifting in its alien seas, from one alien world to 7. Because if there is a single star system that has captured the imagination of exoplanet scientists and sleepy listeners alike, it is TRAPPIST-1, a tiny, cool red dwarf star barely larger than Jupiter, sitting about 40 light-years away in the constellation Aquarius, orbited by 7 rocky planets, 3 of which sit in or near the habitable zone. 7 chances, 7 rolls of the cosmic dice. And Webb has been staring at this system with the focus of a cat watching a laser pointer, trying to determine which of those worlds, if any, might have an atmosphere worth investigating. The TRAPPIST-1 system was first announced in 2017 by a team led by Michael Gillen at the University of Liège in Belgium. The discovery was made using a relatively modest ground-based telescope called TRAPPIST, which stands for Transiting Planets and Planetesimal Small Telescope, a name that is also a nod to the Trappist monks of Belgium who are famous for brewing exceptionally good beer. This is not a coincidence. Gillen has acknowledged the tribute with a smile and noted that astronomy and brewing both require patience, precision, and a high tolerance for sitting in cold, dark rooms, waiting for something to happen. The system made international headlines because no star had ever been found with so many Earth-sized rocky planets, and the habitable zone alignment was almost suspiciously convenient, like the universe had arranged a tasting menu specifically for astrobiologists. But convenience and reality are different things. The TRAPPIST-1 planets orbit extremely close to their star, with orbital periods ranging from roughly 1.5 days for the innermost planet to about 19 days for the outermost. They are tidally locked, meaning one side permanently faces the star and the other permanently faces away, creating a world divided between eternal day and eternal night. The star itself, while cool by stellar standards, is a ferocious emitter of ultraviolet radiation and high-energy flares. Red dwarfs are notorious for this. They throw tantrums, they blast their planets with bursts of radiation that can strip atmospheres, sterilize surfaces, and generally make habitability very difficult. The question Webb set out to answer was whether any of the TRAPPIST-1 planets had managed to hold onto an atmosphere despite this constant assault. The first results were sobering. In 2023, Webb observed TRAPPIST-1b, the innermost planet, using thermal emission measurements during a secondary eclipse, which is the moment when the planet passes behind its star, and its own faint heat signature can be isolated. The data indicated that TRAPPIST-1b has a dayside temperature consistent with bare rock and no significant atmosphere, no greenhouse effect, no thick blanket of gases trapping heat, just a naked, scorched surface baking under the glare of its nearby star. This was not entirely surprising given how close TRAPPIST-1b orbits, but it was still a disappointment for anyone hoping that all 7 planets might be atmospheric candidates. Then Webb looked at TRAPPIST-1c, the second planet slightly further from the star and receiving roughly the same amount of energy from TRAPPIST-1 as Venus receives from our Sun. The results, published in mid-2023, were similarly deflating. TRAPPIST. 1c showed no evidence of a thick carbon dioxide atmosphere, ruling out a Venus-like scenario. There were hints that a thin atmosphere might be present, but the data was not conclusive, and the overall picture was one of a world that had been largely stripped by its star's relentless radiation. The real prizes are TRAPPIST-1e, F, and G, the 3 planets sitting most squarely in the habitable zone. These are the ones where liquid water could theoretically exist, where temperatures might be moderate enough for complex chemistry, where the word habitable stops being a theoretical label and starts being a genuine possibility. Webb has been allocated significant observing time for these targets, and the data is still being collected and analysed. As of the most recent publications, the atmospheric characterization of these planets remains an open question. The measurements are extraordinarily difficult. You're trying to detect the faint chemical fingerprints of an atmosphere around a planet that is 100 times smaller than its star, orbiting so close that its signal is almost entirely drowned out. It is like trying to hear someone whisper in a hurricane while standing a mile away. One quirky detail that adds drama to the TRAPPIST-1 story is the system's compactness. All 7 planets would fit comfortably inside the orbit of Mercury. If you stood on the surface of one TRAPPIST-1 planet, you could see the neighbouring planets in the sky, not as points of light but as visible disks, larger than the Moon appears from Earth. Some researchers have speculated that if life existed on one TRAPPIST-1 planet, the close orbital spacing could facilitate the transfer of biological material between worlds through meteorite impacts, a process called panspermia. Life arising on one planet could potentially seed its neighbours. It is a beautiful idea, though scholars still argue whether the energetics of interplanetary transfer in such a compact system are favourable enough for biological material to survive the journey. There is a historical thread worth pulling here. The idea that planets around other stars might harbour life is ancient. Epicurus, the Greek philosopher, wrote in the 3rd century BCE that there must be infinite worlds, some like ours and some unlike, and that life would exist on those worlds as it does on ours. For most of human history, this was pure speculation, philosophy without evidence. Now Webb is providing the evidence, one infrared photon at a time. The gap between Epicurus sitting in his garden in Athens and a space telescope measuring methane in an alien atmosphere from 40 light-years away is about 23 centuries, and the question is exactly the same. Are we alone? The tools have changed. The wonder has not. You breathe slowly. You imagine standing on the surface of TRAPPIST-1e, the eternal day sky dominated by a bloated red star, the neighbouring planets hanging like lanterns above a horizon you've never seen. You do not know if there is air to breathe there. Nobody does yet. But Webb is listening, and the answer, whatever it turns out to be, is already written in light that left that system 40 years ago and is arriving right now, tonight, on 18 golden mirrors 1,000,000 miles from home. The light from TRAPPIST-1 carries chemistry, and chemistry, if you know how to read it, might carry the signature of something alive, but detecting life from dozens of light years away is not like finding a footprint on a beach. It is more like finding a slight change in the chemical composition of the ocean and trying to determine whether a fish was responsible or whether the tide simply shifted. The field of biosignature detection is built on probabilities, not certainties, and the scientists working in it are acutely aware that the most important discovery in human history could also be the easiest to get wrong. A biosignature, in its simplest definition, is any observable feature that provides scientific evidence of past or present life. On Earth, biosignatures are everywhere. The oxygen in our atmosphere is a biosignature. It is produced overwhelmingly by photosynthetic organisms, and without continuous biological replenishment, it would react with surface minerals and disappear within a few million years. Methane is another. While methane can be produced geologically, through volcanic activity and serpentinization of rock, the quantities present in Earth's atmosphere are vastly amplified by methanogenic archaea, single-celled organisms that thrive in oxygen-free environments and exhale methane the way you exhale carbon dioxide. The simultaneous presence of both oxygen and methane in an atmosphere is considered a particularly strong biosignature, because these two gases react with each other and cannot coexist in significant quantities for long without a continuous source replenishing them. Finding them together is like walking into a kitchen and seeing flour on the counter, a hot oven, and the smell of bread. No single element proves someone is baking, but the combination makes it very likely. Webb is designed to detect exactly these kinds of molecular combinations. Its near-infrared spectrograph, called NIRSpec, and its mid-infrared instrument, called MIRI, can identify absorption features from water, carbon dioxide, methane, ozone, ammonia, and a range of other molecules in exoplanet atmospheres. The technical capability is there. The challenge is interpretation. Because the universe is full of false positives, oxygen can be produced abiotically through the photodissociation of water vapour by ultraviolet radiation, where the light breaks water molecules apart and the hydrogen escapes to space, while the heavier oxygen accumulates. Methane can come from geological processes with no biology involved. Even dimethyl sulfide, the tentative detection on K218b that we discussed earlier, has theoretical abiotic production pathways that are poorly constrained. The risk of a false positive is not hypothetical. It is the central anxiety of the entire field. There is a historical precedent that haunts biosignature scientists like a cautionary ghost. In 1996, a team at NASA announced that a meteorite from Mars, catalogued as ALH 84001, contained microscopic structures that resembled fossilized bacteria. The announcement was enormous. The President of the United States held a press conference. The world briefly believed that evidence of extraterrestrial life had been found. And then, over the following months and years, the evidence unravelled. Other researchers demonstrated that the structures could be explained by non-biological mineral processes. The supposed nanofossils were likely artifacts of the sample preparation. The organic molecules in the meteorite could have been terrestrial contamination. The claim did not survive scrutiny, and the episode left a lasting scar on the astrobiology community. It taught them that the bar for claiming a detection of extraterrestrial life must be extraordinarily high, because the consequences of being wrong are not just scientific embarrassment, but a fundamental erosion of public trust in the process of discovery. This is why Webb scientists are so cautious in their language. When the K2-18b results were published, the team went to great lengths to emphasize the preliminary nature of the dimethyl sulfide detection, and to enumerate the many non-biological explanations that remained on the table. They were not being coy, they were being responsible, because if the history of science has taught anything, it is that nature loves to mimic the signatures of life with the signatures of chemistry, and distinguishing between the two requires patience, repeated observation, and an almost painful commitment to self-doubt. One approach that researchers are developing is the concept of an antibiosignature, which is a feature of an atmosphere that would actively argue against the presence of life. For example, if you detected large amounts of carbon monoxide in an atmosphere alongside oxygen and methane, that would be suspicious, because carbon monoxide is easily consumed by metabolic processes and should not accumulate in an atmosphere with active biology. Its presence alongside supposed biosignatures could indicate that all the gases are being produced by non-biological chemistry. The idea is to build a framework where you're not just looking for evidence of life, but also actively searching for evidence against it, letting the two lines of inquiry converge toward a conclusion. Scholars still argue about how many antibiosignatures need to be ruled out before a positive detection can be considered credible, and the answer depends heavily on the specific planetary context, which is a polite way of saying nobody has agreed on the rules yet. There is a quirky philosophical dimension to all of this that rarely gets discussed in the technical literature, but surfaces reliably at conference dinners after the third glass of wine. What if life exists on a nearby exoplanet but uses a biochemistry so different from Earth's that it produces no recognizable biosignatures at all? What if there are organisms that breathe gases we have never associated with biology? What if the chemistry of alien life is so foreign that we could stare directly at its atmospheric fingerprints and mistake them for geology? This is called the problem of alien agnosticism, and it is genuinely unsolvable with current science. We can only search for life as we know it, because we do not know what life as we do not know it would look like. It is like trying to find a word in a language you've never heard. You do not even know what counts as a syllable. You're lying still now, and the thought is both humbling and strangely comforting. Somewhere out there, right now, Webb is collecting photons from the atmosphere of a planet that might be alive. The evidence might be ambiguous, the interpretation might take years, the answer might be yes or no or something we do not yet have a word for. But the telescope is looking, and in the looking itself there is a kind of faith that feels almost biological, an instinct to reach toward the unknown, to ask the question even when the answer might break your heart. You breathe in. Oxygen, a biosignature, the living atmosphere of a world that learned to exhale. And you wonder who else in the universe is doing the same, from the breath of alien worlds to the birthplaces of stars. Because Webb's infrared eyes are not only peering across billions of light years into the deep past and sniffing the atmospheres of distant planets. They're also looking at things much closer to home, cosmically speaking, and revealing details in our own galactic neighbourhood that were previously hidden behind curtains of dust so thick that visible light could not penetrate them. And what Webb has found behind those curtains is spectacular. Nurseries, stellar nurseries where clouds of gas and dust are collapsing under their own gravity and igniting into new stars, each one a furnace that will burn for millions or billions of years, forging the elements that will eventually become planets, oceans, organic molecules, and, if conditions are right, something that can look up at the sky and wonder where it came from. Nebulae are some of the most visually stunning objects in astronomy. Hubble made its reputation photographing them. The Eagle Nebula, the Orion Nebula, the Carina Nebula. These vast clouds of hydrogen and helium seeded with heavier elements from previous generations of dead stars stretch across light years and glow with the energy of the young stars embedded within them. But Hubble's view, beautiful as it was incomplete. Visible light bounces off dust grains and gets absorbed and scattered, which means that the densest, most active regions of star formation, the places where new stars are actually being born, are precisely the places Hubble could not see into. It is like trying to study the interior of a thundercloud by looking at it from the outside. You can see the shape, you can see the lightning flashing at the edges, but you cannot see what is happening inside where the real action is. Webb sees inside. Infrared light with its longer wavelength slides through dust the way radio waves pass through walls. What looks opaque in visible light becomes transparent in infrared. And when Webb turned its instruments toward the Carina Nebula, one of the largest and most active star-forming regions in the Milky Way, the result was an image that made the front page of newspapers worldwide. The scene showed a ridge of gas and dust sculpted into towering peaks by the ultraviolet radiation and stellar winds of massive young stars nearby. The peaks looked like cliffs at the edge of a cosmic ocean, with a sky full of infant stars glittering above them. NASA called the image the Cosmic Cliffs, which is one of the few times a space agency's marketing department managed to capture the poetry of what the science was actually showing. But beyond the visual spectacle, the Carina Nebula images contained genuinely new science. Webb revealed dozens of previously unknown protostellar jets, narrow beams of superheated gas ejected from the poles of forming stars at speeds of hundreds of kilometers per second. These jets are a byproduct of the accretion process. As gas spirals inward toward a growing protostar, angular momentum and magnetic fields conspire to channel some of the material outward along the rotation axis, creating bipolar jets that punch through the surrounding cloud like needles through fabric. Hubble had detected some of these jets in nearby star-forming regions, but Webb found them in far greater numbers and in far more embedded environments, revealing that the early stages of star formation are even more violent and energetic than previously appreciated. One particularly striking jet extended for over a light year from its source, a glowing spear of ionized gas drilling through the nebula with the quiet ferocity of something that has no idea how beautiful it is. There is a quirky detail about these protostellar jets that connects to a much older astronomical puzzle. In the 19th century, astronomers began cataloguing small, bright nebulous patches that appeared near dark clouds. These were called Herbig-Haro objects, after George Herbig and Guillermo Haro, who studied them extensively in the 1950s. For decades, nobody understood what they were. They looked like tiny glowing knots of gas, often arranged in pairs on either side of a dark region. It was not until the 1980s that astronomers realized Herbig-Haro objects are the visible signatures of protostellar jets slamming into the surrounding interstellar medium. The knots are shock fronts, places where the jet material decelerates and heats up and glows. Webb has now resolved these shock fronts in unprecedented detail, showing complex internal structures with multiple bow shocks nested inside each other like waves from a stone dropped in water. Scholars still argue about the exact mechanism that collimates the jets, meaning how they stay so tightly focused over such enormous distances, and whether magnetic fields or radiation pressure plays the dominant role. Webb has also probed the interiors of dense molecular cloud cores, the coldest, darkest, most reclusive objects in the galaxy. These are the seeds from which stars form, clumps of gas and dust so cold that they radiate primarily at submillimeter and far infrared wavelengths, barely above the cosmic microwave background temperature. Inside these cores, the gas is slowly contracting, molecules are forming on the surfaces of dust grains, and the initial conditions for starbirth are being set. Webb's mid-infrared instruments have detected complex organic molecules in these cores, including compounds like methanol, formaldehyde, and even traces of simple amino acid precursors. This is significant because it suggests that the chemical building blocks of life are being assembled before stars have even finished forming. The ingredients for biology are baked into the process of stellar birth itself. You do not need to wait for a planet to form and a comet to deliver organic molecules. They're already there, frozen onto dust grains, waiting to be incorporated into the next solar system that condenses out of the cloud. One mainstream historical fact that ties this together beautifully is the realization, first made in the 1950s and 60s by astronomers like Fred Hoyle and William Fowler, that every element heavier than lithium was forged inside stars. The carbon in your bones, the iron in your blood, the calcium in your teeth, all of it was manufactured in the nuclear furnaces of stars that lived and died before the sun was born. Carl Sagan popularized this insight with the phrase that we're made of star stuff, which is one of those rare scientific statements that is simultaneously precise and poetic. Webb is now showing that the process is even more intimate than Sagan imagined. The molecules that will become part of future living things are being assembled in the very clouds from which future stars are forming. Life is not something that happens after the universe has finished building. It is woven into the construction itself. You lie here and you think about nurseries, about beginnings, about things so new they do not yet have names. Somewhere in the Carina Nebula right now, a star is being born in a cradle of dust and organic chemistry. And 13 billion years ago, in a different nursery, the first stars were doing the same thing, blazing into existence faster than anyone expected, filling the darkness with light and heavy elements and the raw potential for everything that would follow. The nurseries change, the process endures, and of all the nurseries Webb has revisited, none carries more emotional weight than the Pillars of Creation. You know them even if you do not know their name. 3 towering columns of gas and dust rising like fingers from a hand reaching into space, lit from within and without by the fierce light of young stars. Hubble photographed them in 1995, and the image became arguably the most famous astronomical photograph ever taken, printed on posters, t-shirts, coffee mugs, dorm room walls, and the kind of jigsaw puzzles that people give as gifts when they do not know what else to buy. The pillars became a cultural icon, a secular cathedral, a reminder that the universe can produce beauty on a scale that makes human architecture look like a child's sandcastle. And then Webb looked at them again in infrared and showed us what Hubble could not. The pillars are located in the Eagle Nebula, also known as Messier 16, a star-forming region about 6,500 light-years from Earth in the constellation Serpens. The nebula was first catalogued by the Swiss astronomer Jean-Philippe de Chizeux in 1745, though it was Charles Messier who included it in his famous catalogue of objects that might be confused with comets, a list that was originally intended as a practical tool for comet hunters and accidentally became one of the most important references in amateur astronomy. Messier, incidentally, was so obsessed with finding comets that he reportedly wept when a rival discovered one before him. Historians still argue about whether Messier's contributions to nebula cataloguing were intentional scientific work or an accidental byproduct of his comet hunting frustration, which is the kind of scholarly debate that makes you appreciate the beautiful messiness of scientific progress. Hubble's 1995 image of the pillars was taken in visible light, which means the columns appeared as dark, opaque structures silhouetted against the glowing background gas. You could see the shapes clearly, the craggy surfaces, the wispy tendrils being eroded by ultraviolet radiation from a cluster of massive young stars nearby called NGC 6611. But you could not see through the pillars. Whatever was happening inside them, whatever stars were forming in their dense interiors, was hidden. It was like looking at a mountain from the outside and knowing that somewhere deep inside there are caves full of crystals, but having no way to see them. Webb's near-infrared image changed everything. In the NIRCam view, the pillars become translucent. The dust that blocked visible light is rendered nearly invisible at infrared wavelengths, and suddenly the interior structures are revealed. Newborn stars appear as bright red points embedded within the columns, surrounded by diffuse halos of warm gas. Some of these protostars are still actively accreting material, still growing, still in the process of becoming. They glow with the heat of gravitational contraction, not yet hot enough to ignite hydrogen fusion, not yet truly stars but no longer just clouds. They are in between things, cosmic adolescents caught in the awkward transition from gas to fire. And Webb shows them with a clarity that Hubble could never achieve, each one a tiny beacon inside the dark cathedral of the pillar. The mid-infrared image taken with Webb's MIRI instrument reveals something different again. At longer infrared wavelengths, the dust itself becomes the star of the show, glowing faintly with its own thermal emission. The pillars appear as ghostly blue-grey structures against a darker background, and the young stars that blaze so brightly in the near-infrared view largely disappear. The dust is too thick even for mid-infrared light to fully penetrate in some regions, and those regions mark the densest, coldest cores where the next generation of stars is still in the earlier stages of collapse. It is a layered portrait. Near-infrared shows you the adolescent stars, mid-infrared shows you the embryos, and visible light shows you the architecture of the nursery itself. Each wavelength tells a different part of the same story, like three witnesses describing the same event from three different vantage points. One particularly haunting detail in the Webb images is the presence of what astronomers call evaporating gaseous globules, or EGGs. These are small, dense knots of gas at the tips of the pillars, being sculpted and compressed by the radiation from the nearby star cluster. Some of these EGGs contain protostars. Others are collapsing under their own gravity but have not yet formed stars. And still others are being eroded faster than they can collapse, their material being boiled away into space before a star has a chance to form. They are failed beginnings, potential stars that will never ignite. There is something unexpectedly poignant about that. Not everything that begins gets to finish. Not every seed becomes a tree. The universe is lavish with its raw materials, but ruthless with its selection. There is a quirky and somewhat unsettling footnote to the pillars of creation that has been circulating since 2007. Observations from the Spitzer Space Telescope, another infrared observatory that preceded Webb, detected a large shell of hot dust near the pillars that some astronomers interpreted as the shock wave from a supernova explosion. If this interpretation is correct, the blast wave may have already reached the pillars and begun destroying them. But because the pillars are 6,500 light-years away, the light showing their destruction has not reached us yet. We may be looking at a structure that no longer exists, a ghost photograph of something that was obliterated thousands of years ago. Scholars still argue about whether the supernova interpretation is correct, and subsequent analyses have cast doubt on the timing. But the possibility lingers in the literature like a melancholy whisper. The most beautiful thing in the sky might already be gone. You let that thought settle over you. The pillars of creation, glowing in Webb's infrared gaze, revealing stars being born inside columns of dust that might already have been swept away by a shockwave that left 6,000 years ago. You're looking at the past. You're always looking at the past. every photon that reaches your eyes is a messenger from a moment that has already ended, and somehow, in that delay, in that gap between event and observation, there is room for beauty so immense it makes your chest ache. The pillars rise, the stars ignite inside them, and you are here, in your bed, in the dark, watching it all unfold in slow, ancient infrared light. The pillars glow in your mind as we drift from the nurseries of nearby stars to something far larger, far heavier, and far stranger. Because Webb is not only looking at individual nebulae and exoplanet atmospheres, it is also mapping the invisible scaffolding of the universe itself, the vast unseen architecture of dark matter that holds everything together like the skeleton inside a body you cannot see. And the way it does this is through one of the most elegant tricks in all of physics, a phenomenon so perfectly predicted by Einstein's general relativity that it feels less like science and more like magic. Gravitational lensing, the bending of light by gravity. The idea is deceptively simple: mass-warp space-time. This is the central insight of general relativity, published by Einstein in 1915, and it means that a sufficiently massive object does not just pull things toward it with gravity, but actually bends the fabric of space around it, curving the paths of anything moving through that space, including light. When light from a distant galaxy passes near a massive foreground object, like a galaxy cluster, the light's path is curved. The distant galaxy's image is distorted, stretched, magnified, sometimes split into multiple copies, arranged in arcs and rings around the foreground mass. The foreground cluster acts as a natural lens, a cosmic magnifying glass built not from glass but from gravity itself, and the shapes of those distortions encode information about the mass distribution of the lens, including the mass you cannot see. The dark matter, this is where Webb becomes extraordinary, because the telescope's infrared sensitivity and angular resolution allow it to detect far more lensed background galaxies than any previous instrument. More lensed sources mean more lines of sight through the foreground mass. More lines of sight mean a more detailed map of the mass distribution, and more detailed maps mean a sharper picture of where the dark matter is and how it is arranged. It is like having 1,000 X-rays of the same bone taken from 1,000 different angles instead of just 2 or 3. The reconstruction becomes exquisitely detailed. Webb's observations of massive galaxy clusters like Hubble 2744, sometimes called Pandora's cluster, have produced gravitational lensing maps of unprecedented precision. Hubble 2744 is a cosmic pileup, the result of at least 4 smaller galaxy clusters colliding and merging over billions of years. The collision has separated the visible matter from the dark matter in some regions, because ordinary gas interacts and slows down during the collision, while dark matter, which interacts only through gravity, passes through like a ghost walking through a wall. By mapping the lensing distortions of thousands of background galaxies, Webb has traced the dark matter distribution in 3 dimensions, revealing clumps and filaments and voids that correspond beautifully to the predictions of Lambda CDM simulations. In many ways, these observations are a triumph for the Standard Model. The dark matter is exactly where the simulations say it should be, but not quite exactly. And the not quite exactly part is what keeps people up at night. In some cluster cores, the dark matter distribution is more concentrated than simulations predict. The density peaks are sharper, the profiles steeper, the central masses higher than expected. This is sometimes called the concentration problem or the cusp core problem, depending on which specific aspect you focus on. Lambda CDM simulations predict that dark matter halos should have density profiles that rise steeply toward the center, but eventually flatten into a rounded core. Some observations, including Webb's, suggest that the central regions are cuspier than predicted, meaning the density keeps rising all the way to the centre without flattening. Other observations of smaller systems like dwarf galaxies show the opposite problem, cores that are flatter and more diffuse than simulations predict. The two discrepancies pull in opposite directions, and reconciling them within a single framework has proven stubbornly difficult. One historical tidbit that illuminates the dark matter debate is the story of Fritz Zwicky, the Swiss-American astronomer who first proposed the existence of dark matter in 1933. Zwicky was studying the Coma cluster of galaxies and noticed that the galaxies were moving far too fast for the visible mass of the cluster to hold them together gravitationally. He concluded that there must be a large amount of unseen mass, which he called dunkle Materie, providing the gravitational glue. Zwicky was also, by all accounts, an extraordinarily difficult person to work with. He reportedly called his colleagues at Caltech spherical bastards because, he explained, they were bastards no matter which direction you looked at them. His dark matter hypothesis was largely ignored for decades, dismissed as the eccentric overreach of a cantankerous outsider. It was not until the 1970s when Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies and found the same mass discrepancy that dark matter began to be taken seriously. Scholars still argue about whether Zwicky deserved a share of a Nobel Prize for his insight, a question complicated by the fact that he died in 1974 and the Nobel is not awarded posthumously. Now, Webb is providing the sharpest lensing data ever collected, and the story of dark matter is entering a new chapter. Some theorists have proposed that the concentration discrepancies could be evidence that dark matter is not perfectly cold and collisionless, as Lambda CDM assumes, but has some degree of self-interaction. Self-interacting dark matter models predict that dark matter particles occasionally scatter off each other, which would redistribute mass in the cores of halos and potentially resolve both the cusp core problem in small systems and the overconcentration problem in large ones. The strength of the self-interaction is tightly constrained by observations, and Webb's lensing maps are among the most powerful tools for testing these models. There is a quirky irony in all of this. We built the most expensive telescope in history to look at light, and one of its most important contributions may be mapping something that produces no light at all. Dark matter does not glow. It does not reflect. It does not absorb. It simply warps the space around it, curving the paths of photons from distant galaxies, and we read its presence in the distortions it leaves behind, like reading the shape of a stone by the ripples it makes in a pond. Webb cannot see dark matter, but it can see what dark matter does to light, and in that seeing, in that indirect, inferential, beautifully geometric reconstruction, we are building a portrait of the invisible skeleton of the cosmos. You're sinking deeper now. The dark matter is all around you, right here in this room, passing through you without interacting, without touching, without knowing or caring that you exist. Billions of dark matter particles streaming through your body every second, and you feel nothing. The universe is mostly made of things you will never touch, and yet those things hold everything together. There is a comfort in that, if you tilt your head the right way. The dark matter streams through you. The galaxies are too big, the black holes are too heavy, the expansion rate cannot agree with itself, and now, almost inevitably, someone has raised the most radical question of all. What if the universe is not as old as we think it is? What if the age we've been confidently citing for decades, 13.8 billion years, is wrong? Not a little wrong. Billions of years wrong. It is the kind of question that makes cosmologists reach for the antacids, because the age of the universe is not just a number. It is the cornerstone on which almost everything else in modern cosmology rests. Move it, and the entire building shifts. The standard age comes from the cosmic microwave background. The Planck satellite measured the CMB with extraordinary precision and, by fitting the observed patterns to the Lambda CDM model, derived an age of 13.797 billion years, plus or minus about 20 million. That is an uncertainty of less than 0.2%. In science, that kind of precision feels definitive. It feels carved in stone. And for years it was treated that way. The age of the universe was settled. It was one of the few things cosmologists could agree on without starting an argument. But the Planck age is not a direct measurement. It is a model-dependent inference. The CMB data does not stamp a birthday on the universe like a tag on a pillow. Instead, it provides a snapshot of the universe at a specific moment, roughly 380,000 years after the Big Bang, and you use the standard model to extrapolate backward and forward from that snapshot. If the model is correct, you get 13.8 billion years. If the model is wrong or incomplete or missing a crucial ingredient, the extrapolation goes astray. And this is where Webb's anomalies start to form a pattern that some researchers find deeply suggestive. The logic goes roughly like this. If galaxies are more massive and more structured at high redshifts than Lambda CDM predicts, maybe the universe had more time to build them than Lambda CDM allows. If supermassive black holes reached billions of solar masses by redshift 10, maybe the clock started ticking earlier than we thought. If the first stars formed faster and enriched their surroundings with heavy elements sooner than models expect, maybe the Dark Ages were shorter and the first epoch of star formation began earlier. Each of these anomalies, taken individually, might be explainable within the standard framework with suitable adjustments. Taken together, they point in the same direction: more time, more history, an older universe. In 2023, a theoretical physicist named Rajendra Gupta published a paper proposing a model in which the universe is approximately 26.7 billion years old, nearly twice the standard estimate. Gupta's model incorporates a concept called tired light, an old idea first proposed by Fritz Zwicky, the same curmudgeonly genius who discovered dark matter back in 1929. In the tired light hypothesis, photons lose energy as they travel across cosmic distances, not because space is expanding, but because of some intrinsic energy dissipation mechanism. The redshift of distant galaxies would then be caused not by expansion, but by this energy loss, and the relationship between redshift and distance would change dramatically. Gupta combined tired light with an evolving coupling constants framework, which allows the fundamental constants of nature, things like the gravitational constant and the speed of light, to change over cosmic time. The result is a model that naturally accommodates the existence of massive early galaxies and supermassive black holes without requiring exotic formation mechanisms, because it simply gives the universe more time. Now, it is important to be honest about where this idea sits in the scientific landscape. Mainstream cosmology regards it with significant skepticism. Tired light models have been proposed and rejected multiple times over the past century because they conflict with several well-established observations. For one thing, tired light does not produce time dilation. In an expanding universe, distant supernovae appear to brighten and fade more slowly than nearby ones, because the expansion of space stretches the timescale of the event along with the light. This time, dilation has been observed and measured, and it matches the predictions of expansion perfectly. Tired light models do not naturally produce this effect. Gupta's model attempts to address this by invoking the evolving coupling constants, but the community is divided on whether this is a genuine solution or an ad hoc fix that introduces more problems than it solves. Scholars still argue vigorously about whether the accumulating anomalies from Webb are better explained by modifying the age of the universe, by modifying the physics of the early universe within the standard age, or by some combination of effects that we have not yet imagined? The honest answer is that nobody knows. The data is still coming in, the models are still being tested, and the history of cosmology is full of moments where the community was forced to abandon a cherished number and accept a new one. In the early 20th century, the accepted age of the universe was about 2 billion years, derived from Edwin Hubble's original and somewhat inaccurate measurement of the expansion rate. This caused a deeply embarrassing problem, because geologists had already established that the Earth itself was about 4.5 billion years old. The universe appeared to be younger than its own planet. The resolution came in the 1950s, when Walter Baade and Alan Sandage showed that Hubble had confused two different types of variable stars, leading to a systematic underestimate of cosmic distances, and therefore an overestimate of the expansion rate. The corrected age jumped to over 10 billion years, and the embarrassment quietly evaporated. One quirky detail about age measurement that connects to everyday life is the concept of a cosmic clock. Unlike a wristwatch, which ticks at a constant rate, cosmic time depends on your frame of reference. Einstein's relativity tells us that time passes more slowly in stronger gravitational fields and at higher velocities. An observer near a black hole would age more slowly than an observer in empty space. In principle, the age of the universe could be defined differently depending on where and how you measure it. Cosmologists get around this by defining cosmic time relative to the CMB rest frame, the frame in which the microwave background appears perfectly uniform in all directions. But even this convention carries assumptions about the geometry and composition of the universe that Webb's data is now questioning. You lie here and you think about age, about time, about how strange it is that the universe might be younger than we thought, or older than we thought, or exactly as old as we thought, but behaving as if it had extra time to play with. The clock on your wall ticks at a steady rate, but out there, in the expanding dark, time is more flexible than you imagined. It bends, it stretches, it might even be lying to us, and the Golden Telescope a million miles away is trying to read the universe's birth certificate, character by character, photon by photon, in handwriting that keeps smudging. So where does all of this leave us? You've been lying here, breathing slowly, while the foundations of cosmology have been gently rattled, one beam at a time. Impossible galaxies, stubborn expansion rates, flickering dark energy, premature black holes, stars that ignited too quickly, an age that might not be what we thought. It is a lot. It is enough to make you wonder whether the entire edifice of modern cosmology is about to come crashing down, whether the textbooks are about to be shredded, whether the physicists are about to start over with blank paper and fresh coffee, and the slightly manic energy of people who have just realized that everything they taught their graduate students might have been wrong. But the truth, as is usually the case in science, is more nuanced and more interesting than total collapse. Let us take inventory. Let us walk through the building and check each pillar, one by one, and see which ones are still standing, which ones are cracking, and which ones might need to be replaced entirely. The Big Bang itself is not in trouble. This is worth stating clearly, because popular coverage of Webb's findings sometimes implies that the entire Big Bang theory is being overturned. It is not. The Big Bang is supported by three independent and overwhelming lines of evidence: the expansion of the universe, observed by Hubble in 1929, and confirmed by every subsequent measurement. The cosmic microwave background, predicted by George Gamow, Ralph Alpher, and Robert Herman in the late 1940s, and accidentally discovered by Penzias and Wilson in 1964, remember the pigeon droppings, and Big Bang nuclear synthesis, which correctly predicts the primordial abundances of hydrogen, helium, and lithium with remarkable accuracy. Webb's data does not challenge any of these. The universe began in a hot, dense state and has been expanding and cooling ever since. that much remains solid. What is cracking is the detailed story of what happened after the Big Bang. Lambda CDM tells a specific narrative about how structure grew, how galaxies assembled, how black holes formed, and how the expansion rate evolved over time. It is this narrative, the fine-grained timeline rather than the broad framework, that Webb is challenging. Think of it this way. The Big Bang is like knowing that a house was built. Lambda CDM is like having a detailed construction schedule that specifies when the foundation was poured, when the walls went up, when the roof was finished, and when the plumbing was installed. Webb is looking at the house and saying, the house is definitely here, but either your construction schedule is wrong, or someone used a building method you did not account for. The hierarchical model of galaxy formation is under the most direct stress. The discovery of massive mature galaxies at redshifts above 10 is genuinely difficult to accommodate within standard Lambda CDM without significant modifications. Several approaches are being explored. One is to increase the star formation efficiency in early galaxies, allowing gas to convert into stars more rapidly than previously assumed. Another is to invoke feedback mechanisms that are less effective at suppressing star formation in the early universe, perhaps because the gas chemistry and the radiation environment were fundamentally different from conditions at later times. A third, more radical approach is to modify the dark matter model itself, replacing cold dark matter with warm dark matter or fuzzy dark matter, which would alter the halo mass function and change the predicted timeline of structure formation. Each of these proposals has strengths and weaknesses, and scholars still argue about which modification, if any, can simultaneously explain the massive early galaxies, the supermassive early black holes, and the rapid early chemical enrichment without breaking the things that Lambda CDM already gets right. The Hubble tension remains unresolved, and is arguably the most cleanly defined problem in modern cosmology. It is a single number, measured two different ways, giving two different answers. Webb has confirmed that the local measurement is robust, eliminating several proposed systematic errors. If the tension is real, and it increasingly appears to be, it requires new physics. The proposals range from the relatively modest, such as early dark energy, a brief burst of dark energy in the first 100,000 years after the Big Bang that would change the sound horizon scale used in CMB analyses, to the genuinely radical, such as modifications to general relativity that change the relationship between matter and the expansion rate. One particularly creative idea, proposed by a team at Johns Hopkins University, involves a form of dark radiation, an unknown relativistic particle species that was present in the early universe and altered the expansion history before disappearing. It is speculative, but it fits certain aspects of the data with intriguing precision. Dark energy's potential variability is the newest crack and perhaps the most consequential. If the DSI hints hold up and dark energy is indeed evolving, it would rule out the cosmological constant as the explanation and require a dynamical model, something like quintessence, a hypothetical scalar field that permeates the universe and whose energy density changes over time. Quintessence models have been around since the late 1990s, lurking in the theoretical literature like understudies waiting for their moment on stage. Webb, combined with DESY and future surveys like the Vera Rubin Observatory's Legacy Survey of Space and Time, will provide the data needed to test whether quintessence is real or whether dark energy is something even stranger. And then there are the ideas from the fringes, the ones that most mainstream cosmologists regard with polite skepticism but cannot entirely dismiss. Modified Newtonian dynamics, or EMOND, which proposes that gravity itself behaves differently at very low accelerations, eliminating the need for dark matter entirely. Varying fundamental constants, which would change the physics of the early universe in ways that could accommodate Webb's anomalies. cyclic cosmology models, which propose that the Big Bang was not the beginning of everything, but merely the most recent in an infinite series of cosmic expansions and contractions. Each of these ideas has passionate advocates and significant observational hurdles, and the history of physics teaches us that the correct answer is often something nobody has proposed yet. One mainstream historical fact that provides useful perspective is the story of Lord Kelvin's age of the Earth. In the late 19th century, Kelvin calculated that the Earth could be no more than about 20 to 40 million years old, based on its cooling rate. This conflicted with geologists and biologists who needed far more time for their observations to make sense. The resolution came with the discovery of radioactivity, a completely unknown phenomenon that provided an internal heat source Kelvin had not accounted for. The lesson is clear. When the data and the models disagree, the answer is sometimes not in the data and not in the models, but in a piece of physics that nobody has discovered yet. You are very still now. The inventory is done. The building is standing, but some of the walls need reinforcement, and a few rooms may need to be redesigned entirely. The universe is not broken. Our understanding of it is just incomplete, and that is not a crisis. That is an invitation. The invitation hangs in the dark like a door left slightly ajar, and you can feel the light from the other side pressing against your eyelids. Not the harsh light of certainty, but the soft, diffuse glow of possibility. Because that is what Webb has ultimately given us. Not answers, not yet. Not in the neat, ribbon-tied way that documentary narrators like to pretend science works. What Webb has given us is better than answers. It has given us better questions. And in science, the quality of your questions determines the quality of your future. Think back over everything we have covered tonight. You drifted through the darkness and found a golden honeycomb of mirrors staring into the void. You watched it unfurl, all 300 single points of failure clicking into place one by one, a mechanical origami flower blooming 1,000,000 miles from home. You learned that the first deep field image contained not just beauty, but a problem. Galaxies too massive, too mature, too fully formed for a universe that was supposed to still be in its infancy. Remember those galaxies. They were the first crack, the first polite cough from the universe, suggesting that our models might not have the whole story. You sat with the standard model of cosmology, Lambda CDM, and felt its elegance, a framework that explains 68% dark energy, 27% dark matter, 5% everything else, a recipe so successful it predicted the patterns of the cosmic microwave background with eerie accuracy. And then you felt it wobble, the skyscrapers in the empty field, the sequoia growing from a week-old acorn, the massive galaxies where the model said only seeds should exist. You floated through redshift, that beautiful stretching of light that turns Webb into a time machine. You felt the ambulance siren rise and fall, and you understood, perhaps for the first time in a way that settled into your bones rather than just your brain, that looking deeper into space is looking further back in time, every photon a fossil, every image a memory the universe kept without knowing it was keeping it. You confronted the Hubble Tension, those two stubborn numbers, 73 and 67, each measured with exquisite precision, each refusing to budge, each quietly insisting that the universe expands at a speed that depends on how you ask the question. And Webb, rather than resolving the tension, confirmed it, tightening the screws on a problem that was already uncomfortable. You considered the possibility that dark energy itself might be changing, that the force pushing the cosmos apart is not the steady, reliable constant Einstein reluctantly introduced, but something dynamic, something with its own internal evolution, something that might be weakening or strengthening or doing something so unexpected that we do not yet have the vocabulary to describe it. You watch the first stars ignite in the cosmic dark ages, Population 3 monsters burning through their hydrogen fuel with reckless intensity, seeding the void with heavy elements faster than any model anticipated. And you met the supermassive black holes, those impossible behemoths, billions of solar masses assembled in a few 100 million years, sitting at the centres of infant galaxies like old souls in young bodies, with no clear origin story and no respect for the Eddington limit. You sniffed the atmospheres of alien worlds, water vapour on WASP-39b, methane and carbon dioxide on K218b, that tantalising, tentative, almost certainly premature hint of dimethyl sulfide, a molecule that on Earth means life and on K218b means maybe, possibly, we do not know yet. Please do not get too excited, but also please do not stop hoping. You visited TRAPPIST-1, 7 rocky worlds circling a dim red star, 3 of them in the habitable zone, each one a question waiting to be answered. You peered through the dust curtains of the Carina Nebula and watched baby stars ignite inside pillars of gas. You revisited the pillars of creation in infrared and saw what Hubble could never show you, the glowing embers of protostars embedded in columns that might already have been destroyed by a supernova shockwave 6,000 years ago, a ghost photograph of the most beautiful structure in the sky. You traced the invisible architecture of dark matter through gravitational lensing, reading the shape of the unseen by the way it bends the light of the seen. You entertained the heretical possibility that the universe might be older than 13.8 billion years, that the birth certificate might have a smudge, that the clock might have started ticking earlier than anyone imagined. And you took inventory. You checked the pillars, some standing, some cracking, none completely fallen. The Big Bang endures. Lambda CDM holds in broad strokes but struggles with the details, and the details are where the next revolution will come from. This is how science works. Not through triumphant leaps from ignorance to knowledge, but through a slow, patient accumulation of anomalies, each one a pebble in the shoe of the prevailing theory, until eventually there are enough pebbles that someone has to stop walking and redesign the shoe. Webb is filling the shoe with pebbles, and somewhere, right now, a graduate student or a postdoc or a retired professor who cannot sleep is staring at Webb data on a laptop screen and feeling the first glimmer of an idea that will, years from now, resolve one or more of these tensions in a way that nobody currently expects. That is the pattern. That is how it always happens. Relativity did not emerge from the mainstream. Quantum mechanics did not emerge from the expected. The correct answer, when it comes, will surprise everyone, including the person who finds it. And now the lights dim further. The data fades. The golden mirrors drift silently at L2, collecting photons from the edge of time, and you are here, warm, breathing, safe. The universe is strange. It is stranger than we knew a few years ago, and it will be stranger still when we wake up tomorrow. But strangeness is not something to fear. It is something to marvel at. Every broken model is an invitation to understand something deeper. Every impossible galaxy is a door that has not been opened yet. Every tension in the data is a whisper from the cosmos saying, "Keep looking, you are not done yet. There is more." So let the questions rest for now. Let them settle like snow on a field. The telescope will keep watching, the photons will keep arriving, and you, lying here in the gentle dark, are part of the same universe that produced those impossible galaxies and those monstrous black holes and those pillars of creation and those 7 small worlds circling a red dwarf star 40 light-years away. You are made of the same elements that were forged in the first stars. You are held together by the same gravity that bends light around galaxy clusters. You are, in every measurable sense, the universe looking at itself and asking what it is. And tonight that is enough. Your breathing slows, your thoughts soften at the edges, The numbers dissolve. 73, 67, 13.8, 26.7. They blur into each other like watercolours left in the rain. The galaxies that should not exist fade to a warm amber glow behind your eyelids. The black holes that grew too fast sink gently into the dark, their gravity curling around your last waking thoughts like a hand closing around a candle flame. The pillars of creation rise one final time, translucent now, almost transparent, their dust catching the last infrared light of your consciousness. And the golden mirror, that impossible honeycomb floating in the cold a million miles from here, turns slowly, catching photons from the very first morning of the universe and reflects them toward you. A lullaby written in light, arriving across 13 billion years to find you here, exactly here, falling asleep at exactly the right moment. The universe is not broken, it is just bigger than we knew. And that is the most comforting thought of all. Good night, sleep well. The telescope is watching, so you do not have to.